Hello everybody. Today's topic is a new section, Chapter 4, Unit 2, and it's about solving systems of equations, again, solving systems, with something called substitution, okay? Substitution, which is a new way to solve systems of equations. So I'm going to start with the way that we already know for solving systems of equations. So let's take, for example, the following system of equations. Okay? Let's try that again. Y equals 3x plus 5, and y equals negative 2x minus 1. Okay? Rather than make you go through the entire process, why don't I go ahead and just upload a graph of this system of two equations. Okay? So, taking a look here, alrighty. In purple, I've got a negative slope, so that's y equals negative 2x minus 1. Okay, you can see the y-intercept of negative 1 and the negative slope, negative 2 and 1. Okay. In green, I've got a positive slope, a y-intercept of 5, and a slope of 3. Okay, so I've graphed these two lines. Now, a solution to the system of equations, to review, goes like this. Every single point on the purple line is a solution to the purple line's equation. Every point on the green line is a solution to the green line's equation. There's only one point that's on both lines, and so that point is the only point that would solve both equations, and therefore it would be the solution to the system of two equations. And before, all we did was graph it and find the ordered pair, the coordinates of that point. But this time, if we look at that point very closely, the x-coordinate is not a whole number that we can read exactly from the graph. The y-coordinate is not a whole number that we can read exactly from the graph. And so we don't know what the exact solution to this system of equations is. Okay? And that's what we're going to learn today, is how to solve a system of equations, another method that doesn't depend on the graph, that only depends on using the equations. And I'm actually going to show you a different example first using functions, because I think it makes more sense with functions, and then we'll come back to this, and we will complete this problem as an example of substitution for a method of solving systems of equations. So, leave this down on your paper, and we'll come right back to it in about 5 minutes. So, we've set it up, we know why substitution is important. Now I'd like to give a clear example of how substitution works, and I'm going to do it with functions. So let's have the first function, f, be f of x equals 2x minus 3, so that's the first equation, and the second function will represent with the equation g of x equals negative x plus 6, okay? And we know that these two functions could have graphs, and that those graphs would be straight lines, because they're in the form y equals mx plus b, and we understand how that type of equation works. Okay? So more or less, this is what these two graphs would look like. And f has a positive slope, so f would be our red line, and g has a negative slope, and so g would be our blue line. Okay? And we can see that f has a y-intercept of negative 3, and g has a y-intercept of positive 6, g has a slope of negative 1, and f has a slope of positive 2. Okay? And we can see immediately from the graph where the solution to this system of two function equations is. But I'm going to use this as an example to make substitution makes sense. Okay? So f of x is a function, and f of x is the output. Okay? The output is represented on the y-axis in our graph. And g of x is a function as well, and its output is g of x, represented also on the y-axis of the graph. Okay? And so I'm going to label this y-axis here as the output axis. All right? And I'll go ahead and mark that in green. Okay, this goes all the way back to the very, very first chapter that we studied this year, functions. As promised, they never go anywhere all year long. And so this green axis is the output axis. And everywhere that I look on this graph, my two functions have different outputs. So for instance, here, f of 0, the output is -3. Okay? And here, f of 1 has an output of -1. And you'll notice that here, okay, the input is 3 and the output is 3. And so we have f of 3 equals 3. Okay? This point is the only place where the red function has an output of 3. And the same for the blue function. The blue function has many different outputs, and the blue function's output is also 3 at this point. G of 3 also equals 3. All right? And so what we're looking for is we're looking for the place where the output of f is equal to the output of g. So we're going to set the output of the red function equal to the output of the blue function. And this is the step, this next step is the step known as substitution. Okay? I am going to substitute in, instead of just this symbol, f of x, I'm going to substitute in the entire expression 2x minus 3. I'm going to substitute or replace f of x with the expression 2x minus 3. And I'm going to do the same thing with g of x. I'm going to replace g of x with the expression -x plus 6. And what I can see now is that I have an equation, a single equation, with a single variable, just x. And I can solve that equation, okay, using the equation solving skills that we learned last unit. So for instance, I could get all of my x variables organized on the left-hand side to get 3x minus 3 is equal to 6. I could get all of my constant terms, my numbers, organized on the other side to get 3x is equal to 9. And dividing both sides by 3, I get x is equal to 3. That represents that the input point, x equals 3, should be the place where my two functions come out equal. Okay? And I can show that now, because if I take f of x equals 2x minus 3, and I plug in the input value of 3, I replace the variable x with the number 3, and I get f of 3 is equal to 6 minus 3, or f of 3 equals 3. So the output point is 3. Same with g of x. If I take g of x and I replace the variable x, the input, with the number 3, I get g of 3 is equal to -3 plus 6. And -3 plus 6 is 3. And so what I find is that when I input x equals 3, I get the same output of 3 for both points. And therefore the solution to the system of two equations is input 3, output 3. So x equals 3, y equals 3. And that represents the one point that's on both lines. It represents the one input-output pair that will solve both functions at the same time, or make both function equations true at the same time. And so, I'm going to use that same technique now that I've looked at it in terms of functions. I'm going to look at that same technique for this system, where the input and output pairs are not whole numbers here. The input-output pair, that's the solution to this system of equations. These numbers aren't whole numbers, so I can't really guess them from looking at the graph. So what I'm going to do is I'm going to take my green graph, I'm going to take the green y value, basically, and I'm going to set it equal to the purple y value, okay? And I'm going to substitute in for the green y value 3x plus 5, and I'm going to substitute in for the purple y value negative 2x minus 1. Okay? And this gives me now an equation that I can solve, because it's an equation in a single variable. So if I add 2x to both sides, then I get 5x on the left plus 5 is equal to negative 1. If I then subtract 5 from both sides, I get 5x is equal to negative 6. And then I divide both sides by 5. And I get x is equal to negative 6 over 5. And as a decimal, that's negative 1.2. So that's part of my solution. I now know what my x value is going to be on this point. But the entire solution to this system of equations is not just a single x value, it's an xy pair. So, this is a big and important point. Solving for the x value when you're trying to solve a system of equations is not the end of the process, because remember I'm looking for the xy pair that solves both two variable equations at the same time. So I've only found one of the variables. I now know that this number here for x is negative 1.2, but I still don't know the y value. Well, if I know what the x value is, I can go ahead and plug that x value in here to the green equation, or I can plug that x value into the purple equation. And in that way, I can figure out what comes out for the y value. Okay? So I'll go ahead and plug it into the purple equation. Alrighty. If you give me a moment. Okay, here we go. Did I say purple? I'll plug it into the green equation. So I have y is equal to 3x plus 5. I know my x value is negative 1.2, and so I'm going to replace the variable x with the number negative 1.2. And in that way, I end up, by doing these calculations, figuring out the value 1.4 for y, okay? And actually, I'm going to check it on the other equation too, just to prove a point. I'm going to take x equals negative 1.2, and I'm going to plug it into the purple equation as well. I'm going to get positive, 2.4 minus 1. And you'll notice that when I plug in x equals negative 1.2 to the green equation and to the purple equation, I get the same y value out for both equations. So that means when x is 1.2, y negative 1.2, y is 1.4. Okay? And that's the solution to this system of equations. The solution is given by the two different numbers, the x value of negative 1.2, the y value of 1.4. I found it by substituting in, by taking this y value and replacing it with a whole expression, and that gave me this 1 point. That 1 point has an x value of negative 1.2 and a y value of 1.4. And so this is the one ordered pair that will solve the green and the purple equations at the same time, representing the 1 point that's on both lines.